Hello and welcome back to Let's Code Physics. We are continuing with our development of a rope simulator, the type of simulator you might see in a game like Cut the Rope or Angry Birds or Jungle Hunt or any game where where there's some rope that needs to be swinging back and forth, and maybe the rope is attached at two ends and it needs to be able to level out in the middle, or maybe the rope gets stretched and then cut and launches away. What we're going to start looking at today are some of the different tricks that you might do with a rope in a video game, some of the different behaviors you might expect it to observe. So what we're going to look at is we're going to look at fixing two of the ends and seeing what happens in the middle, how the rope sort of settles out. We're also going to look at what happens when somebody grabs onto the rope and adds some weight onto the end to try to, say, swing across a cliff. First, let me walk you through a couple of technical changes I've made to the code. I have decided to, instead of setting the spring stiffness between each atoms, I wanted to set the stiffness for the entire rope, because if you have the stiffness between two atoms or rope elements fixed, and then you chain more and more of them together, the rope itself is going to get stiffer. What you would really expect to have would be the stiffness for the rope set, and then the individual atoms take on the stiffness of the rope times the number of atoms. Excuse me, the rope would get less stiff as you added more and more on. Sorry, I got my series in parallel confused there. The rest of it is pretty much the same. There's, as far as the setup, there's the spring's natural length, the mass of gravity. I've added in a damping force, but it's currently set to 0, so we're not going to have any energy loss right now. The other thing that I've changed is we now know that the code is conserving the energy. And in fact, once we add in the drag force, it won't be conserving energy, so that wouldn't be worth looking at all that much anyway. But what I would be interested in would be seeing how much the length of the rope changes, right? So, you can think of a rope as kind of, as a very stiff spring. But let's say you had a bungee cord that gave a little bit more, and then let's say you had, some elastic that gave even more. You might even use this to model, for example, silly putty. If you had, the atoms collect in on each other in 3 dimensions, that might be a fun extension for this. But for a video game, for example, you would probably be interested in the rope maintaining more or less the same length, but it's not a simple matter of just going from one end to the other, because it might curve, it might twist, or curve back and forth. So I've added in a calculation of the rope's length, and basically each time it evaluates it updates the springs between the rope elements, it's now going to evaluate the rope length. So this is now taking the place of the energy calculation. I've still got the energy calculation in there commented out in case we want it later. But basically it's adding the length of each spring, because it's already got the length between two atoms calculated, so why not use the information that's already there? And then within each within each run of the loop, I should say, it's going to graph the rope's length versus time. So now we're going to get two windows. So here's our rope animation swinging back and forth. I've got about 30 rope elements connected together here, so it's running a bit more slowly because it's it's having to go through 30 of them. And here's the rope length. You can see it's right at about 15, because there's 30 elements of 0.5 each, so that makes the length of about 15. Actually, I guess it makes it 14, since there's 14 springs for 15 atoms. And you can see the rope length is staying pretty much constant. It's oscillating a little bit because there is a little give to the springs. But here we've got the rope swinging back and forth, and we're establishing that the length of the rope is staying pretty much the same. So this is the rope swinging back and forth. It started out at an initial angle of, I think, about 30 degrees from the vertical. And this is just the effect of, gravity pulling it down, the springs, stretching and compressing around their equilibrium lengths. And you get a motion kind of like this. It is going a bit slowly. I think I've got the rate kind of maxed out here, but let's maybe even put in a couple of extra zeros just in case that helps. I could also decrease the number of atoms, but I think I like it at 30 because it's nice and continuous. So let's take a look at some of the tricks we might do with this, some of the physical behaviors we might want to observe. So for example, right now we've got the one end fixed, and we're sort of starting at an angle like this. Another interesting scenario is the one I've got commented out here, where let's say that you've got the rope initially starting out horizontally. So in this case, each rope element, each atom, is going to have an x position that's a fixed distance from the previous one. So they're all going to be L0 apart, so starting out their nice equilibrium length. But they're all starting at the same height, so the rope is initially completely horizontal. Of course, gravity is going to take it into effect. It's going to make the rope sag. But the springs are going to pull back up, so it's going to oscillate back up and down. I've also got plans to try a little parabola shape there initially, but let's try this one at first. And what I want to do is I want to leave not only the first one fixed, but also the last point fixed. So what I'm going to do is I'm going to come down here. And currently I've got it to where if n equals 1, meaning if I'm at the first atom in the rope, then it's setting the force equal to 0, meaning that atom is not going to move. It's going to stay at its initial position and its initial velocity. Its initial velocity is 0. Its velocity won't change, so it's not going to move. But I can do the same thing with the with the last one. So from 1 to n atoms, they're all free to move, but the first one and the last one are fixed. So it's only the stuff in between that's allowed to move. And I set it up to where I wanted to also add in the damping force, but I think I'll do that in a second. So let's see what happens with this thing not being damped. So you've got the first and the last one being fixed. You have gravity acting on the rope. You can see it's going to be falling down, but then the springs pull it back up. Of course, this is changing the length of the rope, right? So the two endpoints are fixed. It initially starts out at this length, and then it becomes this length, and this plus this is longer than this plus this because the horizontal length is fixed. You notice it's not going back up to its it's not going back up to the original shape perfectly. It's still a little bit wiggly when it reaches up to the top. I can probably even make this bigger. I mean, I can definitely make it bigger. There we go. So you see you've got this sort of wave motion going on while the general up and down motion is going on. So there you've got some peaks and valleys. It almost looks like our wave function time evolver from Monday. But the thing is, without the damping force, with energy of the Earth rope system conserved, this thing will continue to bounce up and down, and it will never come to an equilibrium position. That's where this damping force comes in handy. So let's try a damping coefficient of 0.05. The way a damping force works, if we come down here, and I actually called it a drag force. It's technically a drag force if it goes like the square of the velocity. So let me fix that there. Basically, it's a force that always points opposite of the velocity. So as an object, when these atoms moves through a medium, moves through the air, it's going to have some collisions with the fluid molecules. This could work in air or water, and so those are going to scatter off of there and absorb some of the energy that the atom has, or the ball has, and so that force is always going to work against the velocity. It's always going to work to point opposite of whatever the velocity is. So you just say that it's equal to some constant times the velocity times a negative sign. We're saying the damping coefficient to be 0.05. So let's see what happens with this one. Let's see. So we get the same type of behavior initially. Initially it is flat. It goes down into this V shape, then bounces back up. But you notice it doesn't quite reach the initial height. It doesn't quite come back up there because the damping force, the air resistance, has robbed it of some of its energy. And so you see there it's reaching not quite even the height it had before. And so basically with each oscillation, the air resistance is going to rob it of some energy until it finally comes and, settles down on some, on some equilibrium position. Of course, when we see this in real life, we see it very quickly. If you watch a rope fall down, it's going to have a couple of oscillations. So obviously it's got a much higher damping force in real life. But you can see it's kind of settling in on the type of shape you would expect a rope to have. Let's actually put back in the energy calculation. So rather than doing the rope length, let's actually see what happens to the energy of this thing. Let's get rid of the rope length and get rid of, let's copy this. Energy, and we can comment out that part. Oh my, maybe I have something wrong with the energy calculation there. Oh, you know what? I need to add back in the energy calculation, don't I? So there's the energy calculation. Oh yeah, I only added in half the energy calculation. I didn't add in the other half. Oops. Am I missing any other energy calculations somewhere? Energy equals 0, energy equals that. So this is why you never delete anything. You comment it out because you never know when you might need it again. Okay, so this is losing some energy. It's losing some energy due to the damping force. You notice that it goes in sort of it has these little plateaus because when the thing reaches a velocity of 0, there's no damping force, so there's no energy being robbed. So you notice whenever this thing reaches a turnaround point, whenever the animation reaches a turnaround point, the energy diagram reaches one of these plateaus because at that point it's not losing any energy to the damping force. And of course, each time it's losing a little bit less energy because it's picking up less velocity, or it's picking up less kinetic energy, I guess I should say. Yeah, so this thing, it originally had close to 0 energy. Does that make sense? Yeah, that does make sense because it started out at rest. It was at 0 height and no compression of the springs. So yeah, so this represents the energy lost, basically. And it's kind of leveling out, you can see. So as this thing levels out to a uniform position, this thing levels out to a minimum. So you're approaching an equilibrium. Basically, an equilibrium point is wherever in your energy diagram you have a minimum. This thing's a minimum in the sense that it's not going to get any lower. It's going to flatten out, but that still is a type of equilibrium point. So this is pretty cool. So this is working out pretty well. Of course, we can make things even more interesting as we always do. Let's try giving this Y a little bit more of an interesting initial shape. Let's give it this sort of parabolic shape initially and see what happens. So here I've got it in this shape originally, but what that means is that those springs have been stretched. And so now they're bounding back upward, but then gravity pulls them back, and then they bound back upward again because the springs have been stretched. Again, you get this sort of wave pattern going on in the middle. It's looking pretty decently continuous, so I'm glad I stuck with the n equals 30. But you notice it's not getting as high as it was originally, and that's corresponding to the energy diagram decaying. You notice that even though their shapes are different, so if you compare this energy versus time graph to the last one, even though they've got different types of bumps and wiggles, they've both got the same general sort of exponential decay look to them, and that's from the nature of the damping force. Will give you some sort of exponential graph. It'll be more complicated than that, but somewhere in there is buried some general exponential behavior. General exponential behavior. That sounds like a good physics comic book character. Actually, General Relativity is already a physics comic book character in the Spectra comic books. Highly recommended. So this thing is leveling out there. Cool. Awesome. So this was a pretty fun. This was some pretty fun behavior to display. Of course, in a video game, one of the primary things you're interested in is being able to swing on a rope. So I've made a different code. I didn't want to have to comment in and out too many things. So I made a different code called grabbing rope up here. This has the same setup, so it's the same rope as before, 30 atoms, same stiffness, the same mass. We'll leave out the damping for right now, so we'll have no energy loss at first. But this time we're going to add, and it also has the same starting angle, and we can actually get rid of this part because I copied the previous code. We don't need that in here. What this has now is it's adding in a block. This is going to be a red block. It's going to be located over down and to the left on the screen, and it's got a mass of 9 times one of the rope elements. I'm interested in making this heavier in a little bit, but we'll start out with 9 times one of the mass elements so that when it grabs onto one of the points on the rope, that's got a mass of 10 times one of the mass elements total. And again, it's got a starting angle of 30 degrees, so this is going to come swinging from the right over to the left. And I've got the code set up. This is actually borrowing a little bit from my FTL code, which has proven to be quite popular. Thank you, Redditors, for frequenting the FTL series. I'm going to have to extend that one, apparently. So what I've done is I've set up a condition to try to figure out if the block has sort of grabbed onto the rope. So I've set up this counter in grabbed. It starts out with a value of -1. So a value of -1 means the thing has not been grabbed yet. So if n is less than 0, meaning it's that initial value, The rope hasn't been grabbed yet. Then we're going to check for whether the block can grab onto the rope, which means that some point on the rope ends up overlapping with some point on the block. So what we're doing is we're checking every atom's position, and we're checking whether its X position is to the left of the block's left edge. So the block's left edge is going to be the block's X position, to the left of the block's right edge. Left of the block's right edge, yeah. It's going to be the block's X position plus half times the block's X dimension. So you imagine here's the center of the block, and half of the width of the block over this way is its right edge. And it's going to check for whether the atom's position is greater than its left edge. So that's the same thing, but with a minus sign. And then it does the same thing with the Y. So this is a very long if statement. Again, I sort of figured this part out in the first FTL video. Yeah, in the second FTL video where I actually made the optimizer. So the one that came out last week. Yeah. Here it checks for whether the Y position is less than the top edge and whether the Y position is greater than the bottom edge. Basically, if all of those are true, then that means that that atom is inside the block, and that means it can grab on. So now we're going to set N grabbed equal to N, equal to that atom. And basically what that's going to do is later on when we evaluate the forces on the block, the first thing it's going to do is it's going to update the block's position to equal the position of that atom. So once the block has grabbed onto it, the block is going to follow along with the atom. That's what this part does here, is if it's been grabbed, then you keep the block's position wherever that atom's position is. But what it means is I need to modify the force, because now that there's that extra mass clutching onto that atom, it's going to change that atom's weight force. So we've changed the gravitational force here, where if the atom that you're looking at is the one that has been grabbed, that's basically what that is saying, if N equals the one that's been grabbed, then the gravitational force is equal to the element mass plus the block mass times gravitational field times the times y hat times downward. Otherwise, it's equal to negative mg y hat, just like before. And so let's see, and then of course we've got the drag force in there, but we're going to set that to 0 for right now. And so let's see what happens here. So over here we've got the block, the rope is coming swinging. So you imagine, this is terrible video game graphics, right? So you imagine that this is your video game hero, and he's waiting on the ledge, because you always wait for the rope to come to you. You don't jump when the rope is on the other side. And so you imagine that he's waiting for the rope to come to him. The rope is swinging around. Will it reach it? Will it reach it? I know it's going to reach it. I've tested it out before. So here, one of the atoms overlaps with the block, and it latches on. You saw that little jump there. Not the greatest animation in the world, but it's something. So it latches onto the rope there. So now this little piece of the rope here has an additional mass added onto it. And so now the rope is going to swing differently. You can already tell it's swinging a little bit differently. It's behaving a little bit straighter now because this thing is weighing it down. It's also fun to watch this little tail end down here, because now that's basically swinging more or less freely from the red block there. So the thing is grabbed on, and now it's going to swing back and forth. So now it's changing the way that the rope swings. I need a program in for the block to jump off at some point, but this demonstrates the essential physics, that you're looking for. Let's actually see what happens to this thing if we make that block heavier, because right now that is 9 times the mass of one of the rope elements, and the rope is 30 times that. So let's see what happens if we increase this thing. Let's make the block as heavy as the entire rope. Okay, so we'll make the block mass 30 times the mass of one of the atoms. It's not going to change anything at the initial point, because initially the rope is just swinging on its own. Here the rope comes. Let's see what happens with this thing. So now we've got something much heavier grabbing onto the rope. So you notice the initial part is still the same, so it's always going to reach the block, no problem. Here the block grabs on. So now it's got an additional rope's worth of weight pulling down on it. You notice what's happening to the rope position here. The rope position just got a nice little maximum as it's being stretched out. Oh, it's being stretched out again. So now you can see this thing's kind of, it's almost like this thing is controlling the motion, as it were. So it's like the whole thing is kind of swinging just to support this piece here, the red block. See, this thing is really, keeping it lagging behind there. Oh, that's interesting. You don't see that on Jungle Hunt, do you? So let's increase this thing even more. So let's see. That was 30 times one of the mass elements. Let's make it 100 times. Oh, you know what? Go big or go home. I am home. I'm going to go big. I'm going to stay home. Let's make it 500 times one of the mass elements. Let's see what happens to our rope. Now, I really just want to see this rope just like stretch. It's not programmed to break. I could program the rope to break. Well, this thing is moving. Let me write that down. That's a great idea to make the rope break. Because the rope's obviously going to have some maximum tension. That's a good idea. Make rope break. Y'all keep an eye on that for me. Okay, so here it goes. It's attached. So this thing is 500 times the mass of the rope. Oh my, look at the mass of the rope there. Look at that thing stretching. Oh my, it is not done stretching yet. You can tell it's getting longer because the view is expanding. I need to put in a little grid lines or something in the background so you can better tell the length of the rope. Here it's finally sort of springing back on itself. So this thing went from a length of 14 to a length of 21. So it increased, the length of the rope increased by 50%. I don't think you see that too much on too many video game ropes. So the way you would fix that, for example, if you didn't want it to stretch that much, you would just increase the stiffness, right? So I would increase this thing by, say, a factor of 10. I may need to change the DT on that. I'm not sure. Ideally, this won't change the rope's swinging behavior, but let's find out. Okay, yeah, it should still reach the other side from conservation of energy. So we've increased the rope's stiffness by a factor of 10, so we should not see so great a stretch this time. There we go. The block is grabbed on, so let's keep an eye on our rope length here. Okay, it's still increasing, but you notice it only increased by 1. So it increased by 1 out of 14 instead of 7 out of 14. So if you want your rope to stay basically the same length, you've got to, set the stiffness to be pretty high. Cool. So this has been pretty fun to watch. I think we'll call it a day there. Next time, what I want to do is I want to start taking a look at some other different scenarios. Ooh, look at that! It's getting a little fluttery to it. Again, you don't see that on Cut the Rope or on Jungle Hunt. I want to take a look at some other scenarios. Things like what happens if the weight of the red block is too great. Can we simulate the rope breaking? Can we break the rope ourselves and send the thing launching? So who knows? We might have a primitive a version of Cut the Rope by the time we get done with this series. So thank you so much for watching. I will see you next time. Bye bye.